Chapter 8, Section 5 is on solving these log equations and these exponential equations. So we've spent all this time learning about logarithms, but haven't done a lot with how to actually solve with them. The first way we're going to solve these exponentials doesn't even involve logs at all, actually. It's a shortcut where you look for a common base. Now, common base means where the base of these exponents is the same or can be made the same. So like here for this first example, 2 to the x equals 2 to the x minus 5. Well, if this is true, if 2 to the x actually equals 2 to the x minus 5, the only way that's possible is if the powers themselves are equal. So if 2 to the x equals 2 to the x minus 5, then x must be the same as x minus 5. And in this case, when you solve this one, you're going to get 0 equals negative 5, which means this has no solution, can't be solved. Most of them won't turn out that way, but obviously 2 to the x can't equal 2 to the x minus 5 because whatever x is, x minus 5 will be different. So over here for this one, we have 2 to the x equals 8 to the x plus 3. Well, right now, 2 and 8 are not the same base, but 8 is a power of 2. It can be written as 2 to the third. So I can turn this into 2 to the third times x plus 3, and that's equal to 2 to the x. Now that I have a common base, I'm going to simplify. So 2 to the x equals 2 to the 3x plus 9. I distribute that 3 on top. With the common base, if 2 to the x equals 2 to the 3x plus 9, then x must equal 3x plus 9. We solve this, subtract a 3x from both sides, and x would be negative 4.5. I could show the check of that, but it's going to work out, so let's just move on. Now, this only works if these are powers of the same base, not multiples of the same base. If I had 2 to the x equals 6 to the x plus 3, 6 isn't 2 to some clean power. It's 2 to some power, but not a clean power. This is only a shortcut if you have clean powers to work with, so I'm not going to try and do this one this way. Now, these two here, 1/25 and 1/25, don't look like they have a common base, but you need to start becoming aware of the prime factors of these. You typically want these bases to be prime numbers, although not always. 1/25 is actually 5 to the negative 2. And 125 is 5 to the third. So now I've got a common base of 5. So I'm going to have 5 to the negative 2x plus 6 equals 5 to the 6x. I can drop my bases once I've got the common base, and I just solve this. 6 over 8, which is 3 over 4, equals x. So that's solving the common base. A very common mistake is people will, like, if you come back to this problem here, people will try and take the 8 and or take the 2 and turn it into an 8. They'll say, okay, 2 to the third is 8. But then they're actually changing one side without changing the other side. Notice here, from 8 to 2 to the third, we didn't change anything. 8 and 2 to the third are the same, so I can manipulate the right side without manipulating the left side. But here, if I take 2 and I cube it to try to make 8 out of it, I'm actually changing the left side in a way that I'm not changing the right side, and that's a problem. So that's a shortcut of finding a common base. Do it whenever you can. However, most problems can't get a clean, simple common base. So we've got to solve them with exponentials and logarithms. These are going to be 3 exponential equations. I want to solve them with logs. I want to get the thing being brought to the power by itself. It's almost like that's my variable I'm solving for. So I'm going to subtract 5 from both sides, giving me 4 times 0.6 to the x equals 3. Divide both sides by 3, and 0.6 to the x equals 3/4. Now this is an exponential, and one option is convert to log form. So that's log base 0.6 of 3/4 equals x. And I can just calculate that log using the change of base formula. So I'll do the change of base formula is log of 3/4 divided by the log of 0.6. 0.563. Remember that if you have a fancier calculator, your calculator can probably just take plugging in the base as it is. Your calculator probably has a log base button you can use in the math menu. The other option, and this is the way this is more frequently taught, is to take a log of both sides. So we have the log of 0.6 to the x equals a log of 3/4. If I take a log of both sides, I can now pull this power out in front. That's one of our properties. So we get x times the log of 0.6. This isn't base 0.6, this is base 10. Okay, I did a log of base 10 of both sides. We do base 10 because it's in our calculator. Then divide both sides by the log of 0.6. And we calculate that, which we've actually already done. Log 3/4 divided by log of 0.6 is 0.563. I'm going to check that actually to make sure that it works, just to show how clean this comes out. 4 times 0.6 to the second negative is my previous answer, plus 5 equals 8. Bingo, comes out to 8. So most problems can be solved with converting between forms. There's a couple problems that are kind of a pain to do that way. Everything can be done by taking a log of both sides. So if you want to go about it with taking a log of both sides, that's also always an option. The key is just get the exponential part by itself first. Here's one that's much simpler done just by taking a log of both sides right off the bat, because there's an exponent on both sides. So I start by taking a log of both sides. I can pull the powers out in front, so it's x times the log of 2 equals x minus 1 times the log of 6. Okay, so this power has to come out together in a parenthesis. The fact that it's grouped up is very, very important. If you'd like to, you can think of this as just some number, and you can calculate those numbers. The log of 2 is 0.301. And the log of 6 is 0.778. And this is now just a linear equation that I want to solve. I have 0.3x, I'll call it, equals 0.778 x minus 0.778. I'm going to get the x's together, so I'll start coming down here. I'm going to subtract 0.778 from both sides. So I do 0.3 minus 0.778. And that gives me negative 0.478. Divide both sides by negative 0.478. And we get that x is going to be about equal to negative 0.778 divided by my previous answer, 1.63, we'll say. I'd like to check that. So if I do 2 to the 1.63, that should come out to something really close. When if I do 6 to the, in parentheses, 1.63 minus 1. Yeah, super, super close. Basically the same thing. The only reason they're off by a little bit is because of rounding. Okay, now we're going to solve these logarithmic equations. These also have two ways to go about solving them in most cases. The first way is to convert. I can make this 3 to the 5th equals x plus 4, and then subtract the 4 from both sides, and I've got x by itself. 3 to the 5th is 243, so 243 minus 4 is 239. There, we solve for x. The other way to do it besides converting is to do what's called exponentiating. So I take the initial problem and I take this base and I do both sides 3 to the log base 3 of x plus 4 equals 3 to the 5th. I exponentiate both sides, meaning I make these powers with this base. I basically just do this to both sides. And then, excuse me. The property here is these two things can cancel each other. So you get x plus 4 equals 3 to the 5th, and that's going to get you 239. That trick of exponentiating both sides is the method that works in every case. So here we've got a base 10. So I'm going to do 10 to the log of 2 to the x minus 1, sorry, 2 times x minus 1 equals 10 to the log of 4x minus 5. And now these undo each other, they're inverses. So we have 2 times x minus 1 equals 4 times x minus 5. So 2x equals 4 and x equals 2. And that's all great. It's beautiful. It's a wonderful way to solve these things. Obviously, if we check this, we're going to get, if we plug in a 2, this becomes 2 times 2 is 4 minus 1 is 3. So log of 3. 2 times 4 is 8 minus 5 is 3 equals log of 3. Obviously, log 3 equals log 3, so it works. But what's a little bit simpler here is you can just kind of think about the logic of this. If this here is equal to this here, the only way that's possible is if the stuff inside of these functions, these inputs, are the same. You can actually just immediately go to dropping the logs and solving. 2x minus 1 equals 4x minus 5, and solve that from there. This third one here has 2 logs on one side. This is where these properties of logs become so important. I can't convert this, I can't exponentiate both sides, but because they have the same base, I can combine these logs into one, I can simplify. So first I'm going to pull these powers up, and that gets me the log of x squared equals the, or plus the log of 9x squared equals 2. Okay, I had to square the 3 and square the x. Now by properties of logs, these can combine. So I get the log of 9x to the 4th equals 2. These multiplied to combine these logarithms. It's a property of logs, so I have this. Now I can convert or do both sides to the power of 10. I'm just going to convert. This is 10 to the 2nd equals 9x to the 4th. So 10 to the 2nd equals 9x to the 4th, which means that 100 equals 9x to the 4th. And now I just solve this equation. I get 100 over 9 equals x to the 4th. So x equals the 4th root of 100 over 9, whatever that is. Usually when you take a 4th root, you do a plus or minus, but we actually know that this can't come out negative. We can't have negative numbers here inside of our functions. So it's whatever that number is, and we can calculate if we wanted to, but I don't really care that much. Sometimes these will come out to quadratics that have to take the quadratic formula and solve from there, but we've learned how to do that. Sheesh. Okay, stop. Keep up. Just erasing, just erasing, just erasing. So now we can start solving word problems like this that actually have some importance to us. So we've talked about compound interest. So say you have $4,500 invested in an account that pays 5.9% annual interest compounded quarterly. How long until the account is worth $9,000? That means how long until the account doubles. Here's the compound interest formula. Y equals P times 1 plus R over N to the NT, where P, R, N, and T are your starting amount of money, your interest rate, the amount of times you compound in a year, and your time. Well, this now can be solved. We plug in 9,000 for Y. We're going to plug in 4,500 for P. 0.059 over 12 is our N, our T. Do the 12 times T, because we don't know how much time this is going to take, so T up there is our variable. Well, like I said before, our goal is to get the power and the base and the power by itself. So I want to isolate this part first, then start logarithming and stuff. So the first thing I'm going to do is divide both sides by 4,500. And that actually just gets me the number 2 over on the left side. Because remember how I said we're trying to see how long it takes the money to double? And the kind of cool thing about this is it doesn't matter how much we start with. It could be $1, it could be $1 million. It could just take the same period, it's going to take the same amount of time for it to double. Now I can either convert this or take a log of both sides. I think I'll just take a log of both sides. So the log of 2 equals the log of whatever all that stuff is to the 12t. I'm not going to write it over and over. I can now bring the 12t out in front. I get that the log of 2 equals 12t times, again, the log of whatever that number is, which if you wanted to, you could calculate, but I wouldn't round that decimal. Rounding is really dangerous. It can, because any decimal makes a big difference, it can actually all throw you off. So don't round as you do this. Keep things stored in your calculator. I'll now divide both sides by 12. The log of whatever that was, I'll write it this time, 1 plus 0.059 by 12. So that's going to cause these 12s to undo each other and these logs to undo each other. And on the right side, I'm just going to be left with t. On the left side, I've got a quick little calculation to do. I'm going to do the log of 2, and do the log of 2 divided by, in parentheses, I'm going to have to do 12 times the log of 1 plus 0.059 divided by 12. And that gets me 11.77. It's going to take about 11.77 years. There's this thing in finance called the rule of 72, which tells you how long it takes your money to double. It's a quick, rough estimate of how long it takes money to double. If you want money to double, you just take your interest rate and divide it by 72. Nope, other way around. Do 72 divided by your interest rate, and don't do that as a decimal, just do that like here, it was 5.9. I do 72 divided by 5.9. I'll just do that in my other calculator here on the side. That's 12.2. So that estimates it'll take about 12.2 years for your money to double. Turns out it was 11.7 when we calculated it, and so it's a little bit off, but it's a very good close estimate. The rule of 72 is take the number 72 and just divide your interest rate or do 72 divided by your interest rate. Okay, we got one more word problem to do. So here's our last word problem. Beryllium-10 is an isotope that has a half-life of 1.39 times 10 to the 6 years, which, if you see that number and that stresses you out, just think about it as, that's in scientific notation, put it in standard form, that's 1,390,000 years, which is an awful long time. It says how long until 10% of the initial mass of the beryllium is left. Well, we've been dealing with this equation for half-lives. Y is your ending amount, A is your starting amount. This is the half for half of the amount that remains, time divided by half-life. So we want to know how long until 10% of the initial amount remains. Well, we don't know what the initial amount is, so we can still just call that A. The nice thing is we know that we want 1/10 of A left over. The question of time means our variable is t, but we know the half-life is this real big number. And the cool thing here is, even though I don't know the starting amount, I can still calculate how long it'll take to get down to 10% of it. So that means if I started with 5 grams or 50 grams or 5 million grams, it doesn't matter. To get down to 10% will still take the same amount of time. Because the first step in solving this would be to divide both sides by a. And when you divide both sides by a, you're going to get 1/10 equals 1/2 t divided by 1,390,000. Now I'll take a log of both sides, or convert to log form, whichever you prefer. I'll take a log of both sides. The log of 1/10 equals the log of 1/2 to the t divided by 139,123 zeros. This power comes out in front as a multiplier. So now it's the log of 1/10 equals t divided by 139,123 times the log of 1/2. I'm going to solve this for t. I've kind of switched colors around, which is sort of weird. I'm going to go back to light blue again. I'm going to divide both sides by the log of 1/2. And I'm going to multiply both sides by that half-life. That's going to leave me just t over here on this side. And the other side I'll calculate. I'm going to do this off screen on my, real calculator. So 1,390,000 times the log of 1/10 divided by the log of 1/2. And that comes out to 4617480. 0.05, which I'll just call it that. So it's going to be about 4,600,000 years is how long it takes for 10% of this to be left. Now I want to see how many half-lives that is. If I take this number here and divide it by this number here, that's 3.3 half-lives. And I'm just checking to see if that makes sense, because we have 100% of the stuff, and after one half-life is 50. After the second half-life, so there's one half-life, the second half-life is 25%. The third half-life is 12.5%. So it's going to be a little bit more than 3 half-lives, which makes perfect sense. If it's a little more than 3 half-lives, it's 4,600,000 years. There, we can now solve equations that are both logarithmic and exponential. Look for a common base, convert between log and exponent forms, take logs of both sides or exponentiate both sides. Use the properties of logs to simplify when you need to, and remember that every solving problem can be checked by just plugging in your answer, which is pretty great. Boy, that was a long one. What's this guy thinking, making a video that takes like 6 hours to watch? And then now we get, again, distracted. Thanks for watching. I hope it wasn't too bad. Please like it, share it, subscribe to it, all those things. Tell your friends. Have a nice day.